Okay, hello everyone. Welcome to the last lecture by Dr. Tousik Samui, and he will be continuing his discussion on interaction picture, I believe.
Okay. Uh,
It's on.
okay. Since this is my last lecture, let me recapitulate what Ratul and I did for the last 7 lectures, and try to put all the things together that we have already developed, and try to see some of the computation for physical processes. Okay, so let me um, just recapitulate a bit that what we did is, so what we did is, like, we started with free field theory. Okay, free field theory, and for scalars, uh, fermions and vectors. Okay, and then what we do, okay, so in this, basically what we have, some Lagrangian, and then we try to quantize the theory. Okay, so quantizing means that promote the fields uh, and the conjugate momentum to operators with appropriate commutation relations. Okay, so that was the second step, and then we went uh, to went to the interaction picture. Okay, so that was the last lecture. That then we introduced interaction terms and started discussing the field and evolutions in the interaction. In the interaction picture. So that is what we did. And then we saw that in this interaction picture, the thing that appears very naturally is the time ordered operators. Okay. So by time ordering, we mean if we have fields phi1, phi2, and then phi n, it basically says that operator with operators at later time sits to the left. Okay, so that's the time ordering that we define. Okay, and then we saw, and like I stated, not exactly proved, that this time ordering operator it has a connection with the normal ordering operators. By normal ordering, we mean normal ordering. So this is, let's say, ordering means the creation sorry, let's say O1, O2, and On is basically creation operators to the left and then followed by the annihilation operators. Okay, so this is the thing that we did, and then we also defined contraction as follows: that if we have few fields phi 1 and then let's say phi I and then phi j operators and then phi n, then contraction between I and j means that we will replace I and j, we'll just remove I and j and put a delta Feynman propagator, and then we'll write the whole thing again, but this time without phi I and phi j expression. So contraction always happens with a pair of operators. Okay, so with these three things, we had like shown that not exactly shown, but stated that time ordering, okay, phi n, can be written in terms of the normal ordering, which is useful when we do the computations, okay, as normal ordering of all the operators and all possible contractions. Okay, so that's the thing that we stated last time. All possible contractions, meaning that this is the term with zero contractions. Then all possible means one pair contraction, two pairs, then so on and so forth. If there are like in number of particles, in number of fields, then n over 2 pair contractions. Okay, so this is the thing. We saw an example with four fields that they give rise to many contractions last time. Okay, then we said, okay, let us try to see an example theory where we defined that the Lagrangian, so it's a theory with scalar Yukawa theory, where we tried to see the utility of this thing that we defined. Okay, so this theory, what we said that we have two scalars. Okay, now one is psi, another is phi, and they have mass terms, and then phi squared. These are the mass terms. So not minus sign. This comes with a plus sign. Sorry, this comes with a minus sign. And then we introduce interaction term, because this is very important for the thing that we are going to discuss. Okay, so this is essentially this with this minus sign. This is the L interaction term. Okay, so then we said that, okay, so now as before, we can promote the fields to the respective operators, then in terms of the creation and annihilation operators. So then we already defined in the interaction picture, this operator takes the form as dqp over 2 pi whole cube 1 over, so this is the normalization, and then b t e to the I p dot x plus dagger it will be minus I p dot x. Okay, and then the dagger field psi dagger will take the form as the 1 over 2, and then this will be cp to the ip dot x minus ip dot x, and phi operator. So these two are, as we remember, these are the complex scalar field, and this one is real. Okay, meaning that this creation annihilation operators are different for the complex scalar, but in the if we impose the reality condition on any complex scalar field, then this creation and annihilation operator are basically conjugate of each other. Okay, so that's the difference between the real and complex field. Okay, so 2ep, and since this is a real field, it is ip dot x plus ap dagger to the minus ip. So that is what I think I made a mistake. So in the interaction picture, the sign actually reverses the sign. So that is what we saw. Okay. Is it, see whether that's correct. Does the sign reverses? The sign reverses, but okay, so annihilation was with plus. Comes with the positive. So it was correct. Actually. That's why 5 minus as well. Okay. Yes. So now what we will see that we are, as we said last time, let us see that we are now interested in kind of let's say we are interested in, let's say, finding the probability of evolving a state I, let's say initial state represented by I, to a particular final state. Okay. So meaning that, let's say, for example, in this interacting theory, let us say we are interested in psi field evolving to psi field. Okay, so this is, let's say, initial state, and this is the final state. So I in this case would be that, let us say, the initial state has a momentum p1 and p2 to same fields, so it will be 2 p1 and then they are created by p1 dagger and then p2 dagger. As Ratul pointed out, that we can actually create this field out of vacuum by these operators, and these are the normalization factors that we have. And then final state is also the same, but with a, let's say, different momentum. Let us say this is p prime, p1 prime, and then p2 prime. Dagger. Notations are getting missing. Okay. So now if we want to see the probability of evolving this, so as we already saw that from a state at, let's say, time t0, or let's say in this case t minus, it evolves via the operator let's say at a later time t plus by the operator e. Okay, and then if we want to find the probability of this state in the state f, then what we have to do is basically do this and take the mod square. Okay, so that is what we are interested in. Okay, by suitable normalization factors. Okay, so there will be some normalization factors. So that is what we are kind of interested in. Now we assume that t minus is at a very early stage, that is at, let's say, minus infinity, and t plus is at a very later stage. We can take it to be plus infinity. Then at this minus infinity and plus infinity times, they're essentially free state, and that is why we can actually create them from the vacuum with the creation annihilation operator from the free field. But in between, they kind of interact and gives rise to something else. Okay, so that's the idea. Okay, now if we remember from the last expression that t plus and t this unitary operator or the evolution operator is nothing but time ordered time ordered time ordering of the operator exponential minus I integration t minus 1 to t plus and dt prime and h I at t prime, where h I t prime is nothing but h interaction at t prime in the interaction picture. Okay? The interaction picture. And if we now want to see that this H interaction is nothing but minus the Lagrangian interaction, where the Lagrangian interaction is given by its Lagrangian density d cube x and right? So if we remember that this Lagrangian that we were writing, it is not exactly Lagrangian, it's a Lagrangian density. Okay, so this one. Okay, so then in this so if we club all these things together, then h in I t prime is nothing but let me write it down as d4 okay, so d4 x sorry, this one d prime. So this whole thing that we are trying to calculate now is so this will be here, and then this will be psi star I x psi x I phi. All these are in interaction picture, right? And operator, so it's no number. This will be dagger. Okay? So this is the thing. Now let us try to compute this quantity that we are interested in. Let us not take the mod for now. So it's like u t plus t minus and I. Okay. So let us see that. Okay, so let me first write the. Okay, so let me write the expression. For t plus t minus. Okay, this is first term is this identity. This is in exponential, and then there is no like meaning of time ordering here, so I'm not writing it. And then the second term would be IG, and then time ordering of integration d4x psi I dagger x and phi. So this will be our second term, and then the third term would of course be whole square over 2 time ordering, uh, and then it will have two integrations d4 x1 d4 x2, let's say, and then psi I dagger x1 psi I not dagger here. And then since it is within time ordering, whether it's x1 x2 does not matter at this moment. So this is our second term, and then there will be other terms also. And now, since we are doing it in the perturbation theory approach, we know that we are not, it is unlikely that we'll take the whole series. Rather, we are kind of interested in first few terms. Okay, and we assume that the coupling this G is small enough that first few terms will give us important information already. Okay, so that is the assumption that we will take, and then we will proceed from here. Let us take the first term. Okay, so the first term is this one, identity. Let us see what happens if we take the first term. So then with this first term, it's like if identity and I. Okay? So if we now calculate this, okay? So now if we calculate this, this is f is 0, and then if we remember the expression for if I and f, initial state and final state, okay, here, then it will be, remember b dagger b dagger b dagger b dagger from the, okay, b dagger b p prime b p 2 prime, then b p1 dagger b p2 dagger, and identity does not. Now we have to do some computation, and we remember the commutation relations that b p for any let's say q dagger is nothing but so this is the relation that we have, and then if we try to swap this, then it will be become bp1 dagger bp2 prime plus 2 pi whole cubed delta cubed and p2 prime minus p1. Okay, so let me write it. So 0 p1 and then dagger prime and then dagger 0 plus 2 pi course have the normalization factors that I have written here. Okay, so then we have the normalization factor that we write it as n, where this normalization n is nothing but the multiplication of these two, this and this. Okay. And then the second term will give me 0, then 1 prime, and then the dagger 0. Okay. Now the second term, if we see that this is nothing but p1, so b, let us say, and this is p2, right? And then with appropriate normalization, okay, so this is not exactly p, so this is actually 1 over square root 2 e p1 prime, but because of the normalization that we define, and p2 also carries a similar term, which is square root 2 e, right? So these are the normalization. If you remember that our states were created with this normalization, okay? And then you have the normalization here also. Now again, the same thing that we will do for the first term that we did in here, okay? So we will, let's say, swap these two, then I will have bp1 dagger and then bp1 prime, okay, plus 2 pi whole cubed delta cubed p1. Okay? So this whole term, and now if you see this term especially, okay, so if you see this term, then it will actually annihilate the vacuum state on the left. Okay, so this, when it acts on this, it will give us 0. Okay, so this is not important. Then we will have this normalization and then 2 pi whole cube delta cube p1 prime 0 bp prime dagger 0, right? And then the second term as p1 prime p2 times let's say, let me write the normalization factor as p1 p2 removed, so it will have only p and p2 prime and then 2 pi whole cube delta cube p1 minus. Okay. So now if you see this term, this is nothing but p1 was k bra and then p2. Okay. And similar way, the first term can also be written in terms of this, and then the final expression boils down to you. The left we want p2 prime. This one is This will be P1 prime, and second term P2 prime. So this is the thing that we are getting from the first term. And now if you actually just draw a quick pictorial representation, then we'll see that this first term is nothing evolving from P1 state to P1 prime state, and they can only go to that state if their momentum is same. Okay, and the second term and the second multiplication term is also the same, that P2 going to P2 prime, and they can only go to that. It is non-zero if P2 and P2 prime are different, are same. Okay, so then only they can evolve. Okay, so this basically says that, let's say pictorially, if we want to see, it is like P1 going to P1 prime with the condition, because of the delta function, that it is essentially going from one to other. So it's basically stays the same. Okay, so, and it can be in a different way, that P1 from the second term, it is P1 to P2 prime, and P2 to P1 prime. Okay, so it's just the combinatory thing. Okay, so but the thing is that this is basically says that the field is just evolving as a free field. Okay, and hence these are not the interesting part that we are looking for. Okay, so this is expected, because the first term we don't have from the identity, we don't have any interaction. So it is expected that no interacting term. So it is expected that they are basically staying as a free field with the same momentum. Okay, and so that's the first term. But then if we go to the second term, then we can let us see that whether some interaction emerges, at least for this process. Okay, so for the second term, okay, let's say if, and we have a minus ig sign, ig time ordering of d4x psi dagger ix ix phi x, and then I. Okay, and now remember, I is nothing but dp1 dagger dp2 dagger 0. Okay, and if has the form these are primes. Okay, so this we have for this particular initial and final states. Okay, so now, and if you remember this one, this phi is combination of AQ, let's say, plus AQ dagger. Now commutation with of this AQ and AQ dagger with these, they actually commute. Okay, so then so this is plus sign. So when we take this term, and then let's say we commute with B first B dagger and then second B dagger, they will easily commute. It will pass through, and then it will act on this vacuum state, and it becomes 0 from this term. And the second term, the same trick we can apply, but now this time, let's say with the psi, all these things, but it can easily pass through, since we don't have any A in this psi dagger, and it will eventually reach here AQ dagger, okay, to near to the 0 state, and it will annihilate this. Okay, so this basically says the second term is essentially 0 for the thing that we are considering. Okay, it might have significance in some other processes where the initial state and final state has something different, but at least for this we don't have the contribution from the second term. But let us see the third term. Okay. Third term is now kind of a difficult, I mean, not a difficult, but it's so I have time ordering, then d4 x1, d4 x2, then psi I dagger x1, 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 and then we have psi dagger x2, psi I x2, x2. Okay, and then so now with this time ordering, we have already said that we can write it in terms of the normal ordering and their contractions. Okay, so this is essentially minus ig whole square over 2 if, and the normal ordering of this all psi phi, psi phi, and then the step. Now, let us notice one thing before calculating this. Okay, so let us notice a property. Okay, if let us say I have bunch of operators in between I and f, initial and final state. Okay, so let's say those bunch of operators are b dagger, q2 dagger, bq3 dagger, and then this q in I. Let's say number of operators. Okay, so this one is nothing but this with proper normalization. This actually not exactly same, but is with appropriate normalization with some constant factor. This is bp1 prime, bp2 prime, bq1 dagger, bq2 dagger, bq3 dagger. Right, so let us for the moment take I to be as it is. Okay, so now if we apply the commutation relation here, okay, just like this, so it will become bq1 dagger, b2, right, and then plus the delta function. Let me write it in a shorter notation. This way of write. Okay, so let me write it as delta prime q1 prime. But this means the whole it's basically 2 pi whole cube and delta cube between p2 prime. Okay, the whole thing. And so this is great. Then it will be 0 bp1 bq1 dagger bp2 prime, then bq1 not q1 anymore, q2 bq2 dagger, bq3 dagger, and so on and so forth, bqn dagger, right? Plus the delta part, that is delta P2 prime Q1. Okay, and I have P1 prime and then PQ2 dagger, PQ3 dagger, and PQ0, right? So this term actually has two less, one less creation operator, one less annihilation operator. But the first term still has the full set. Okay. Now again, just like before, if we swap this thing, okay, swap these two, then we'll have B dagger in front, B, and then some delta functions. Okay, so then B dagger will annihilate. So first term will go to 0, and only thing that survive is 0. Then the delta function between P1 prime Q1 it is everything this time. Okay, let me then stop now and take some questions, and then I'll come back to this. Hello.
Yeah.
Mhm.
I'll pause
Yeah,
there. I've started the recording again.
is it being shared? No. Okay, so it got erased, but I wrote down the important thing that okay, so we were like kind of trying to compute this if and I, where if and I are like created with to momentum with B dagger, yes, BP1 dagger, BP2 dagger, and F is also created with BP1 dagger and BP1 prime dagger and BP2 prime dagger. Okay, so now what we are trying to see that usually in a normal ordered operators, I mean the bunch of operators, we have the um, creation to the left and the annihilation to the right. And let us take a bunch of operators and try to see that what it gives rise to. Okay, so after a few calculations, we reach that there is a delta function, and we still don't have 0 things in here. So now if we swap these two, okay, we'll get a delta function, and then the dagger will come in the front, and that will annihilate the 0 state, the vacuum state. Okay, so eventually from the first term we'll get this P1 prime Q1 and delta of P2 prime this time and Q2, and then we have all this bunch of operators that we already not high here. And then again from the second term we'll have a similar thing, delta of P1 dagger, sorry, P1 prime and Q2 between these two, and then we have the same BQ dagger and other. Now notice that if we have B3 dagger, another extra dagger operator, it will make it 0. right? If you don't have this, all rest are all let's say um, annihilation operator, then we don't have a problem. So this will survive, at least from the left, this will survive only if, since we in the final state. So one thing that we notice, that since in the state F we have let's say two creation or creation, only operators operator with exactly two the daggers has non-zero. Right. Okay. Similarly, for the annihilation state, sorry, for the initial state, I, since it has exactly two creation operator, uh, any normal ordered operator in between uh, non-zero value if that exactly two two annihilation operators, right? So that is an important thing that we notice, that exactly if we have exactly two in this bunch of operators, in this let's say here in this bunch of operators, since initial state has two particles, so two creation operators, and final state also has two creation, or in the brass state it's annihilation. So exactly uh, the operators that will survive in between is should have exactly two creation operator and two annihilation operators. So now if we come back to our third term of the expansion of u t plus t minus, third term of it, then we will see that it had, if let me normalization psi psi phi plus contractions, then I. So out of all the operators that we can calculate get from here, only surviving operators uh, should have uh, two B daggers and two Bs. Okay? And rest will actually not contribute to this. Okay. So now if we want to see that, first of all, any free phi's will not survive. So then what we have to do is, like, we have to only thing that will survive is four psi's, okay, and phi should be contracted out. Okay, otherwise it will not survive. That we saw last time. Okay, so only surviving operator, let me write it, surviving thing is if the normal ordering of psi dagger I x one, we have the integration one, okay, and then psi x1, psi dagger x2, okay, and phi, and then we have to have the contraction of the phi x1 minus x2. So that is the only surviving term that we have. Now, again, from this, only B is not the C operator in it. So if you remember the psi, okay, so we have pi whole cube, 1 over square root 2 E. We have B, and only surviving part will should have the B at least for this case. So the plus sign, and from side dagger we will have so this is the only surviving part. These will be the only surviving part. So if we now take the normal ordering, so we can see that only psi dagger will contribute and via B dagger operator, and psi I will contribute via the annihilation operator, and then our expression becomes very simple, and minus Ig squared over 2, and then we have if, and then we have we have full integration over 4 of the integration from this psi I and psi I dagger. Uh, and then, of course, we have whole if BQ 1 dagger, BQ 3 dagger, and BQ 2, BQ 3, I, and then we have all the exponentials, that is I Q1 x exponential minus I Q2 dot x. So first two are x1s, and then the second two are x2s. Okay, so all these will contribute. And now, as before, if we do this thing, we have done it quite several times, then we'll see that it will eventually give us, just like before, two delta functions, and then some numbers. Okay, so if we actually calculate this, then it will finally become d4x1, d4x2. Then the whole thing will, so we also have the Feynman propagator here for, so this will eventually give us g whole square over 2, and then the integration over all this thing cubed square root 2, and we have this delta functions p1 prime minus q 10 to pi whole cubed delta q, and this is q1, then okay, so this is first term, and then by the way, this is not a commutator. So this algebra we have done several times. So I'm just giving 0, and then we have the Feynman propagator for the phi field. Okay, so this is the thing that we'll get finally in the end. Okay, so not this 0 anymore. I don't have that. And then putting everything together, if we let's say integrate it out with respect to q1, q2, q3, q4 variable, all these 4 variables, because they have the delta functions. Okay, so we'll get eventually we will get minus ig squared over 2. We have, of course, this. It's 2, and we have the Feynman propagator, and then from this we will get okay, so I actually forgot to write one more term here. It's like this term, and there are 2 more delta functions. Let me write the shorthand. P1, Q2, delta of P2. So this is the shorthand that I was using. Q4 plus delta of Q4. So then this thing. So 2 delta functions here multiplied by another 2 sets of 2 delta functions. And if we calculate this, it will be I p1 prime dot x prime plus prime dot x to prime plus e to the power I dot x to I e to prime dot x to this times, so this is first from the first delta function, and then minus I p1 dot x1 minus I dot x2 plus e to the minus I p1 dot x2. So we had the bunch of exponentials. These exponentials are there, those are giving rise to this. Okay. And then if we actually calculate this will be square root 2. Let me expand the delta function in terms of, sorry, the Feynman propagator in terms of a different table. Is it to the I k dot x1 minus x2? So basically remember, and then I epsilon, and then we have all the exponentials. Okay. And now if we integrate over x1 and x2 variable, we will finally get the 2 factor will go away, and we'll finally get b4k over 2 pi whole power 4 pi, and it will be delta 4 p1 9 minus p1 is a 4 vector 4 delta, and p2 prime minus p2. Please do this exercise to see. Right. Okay, of course, this is very like a tedious job to do all these calculations, but thankfully we get a very nice and interesting result that we can kind of see it pictorially. Okay, so for example, for the first term, what it is saying that it is eventually representing p1, p2, this p1 and p1 prime going to, so that is the momentum conservation that we can think of. That okay, so p1 was what? P1 was, let us see it pictorially, that p1 is the initial state, is one of the initial state, and it has a momentum p1, and p1 prime is one of the final state. Okay, and k is basically momentum. If we remember that it actually comes from the delta, the Feynman propagator, it represents the momentum of the phi field. Okay, so some psi, so this one, and the other term is similar, and we can represent it like this. Okay. And it essentially says that this is the contraction that we can represent it, via something of this. So this represent the contractions, that is the Feynman propagator, and the other things are represented by this lines. Okay, so now we'll see that now by drawing this line and appropriately remembering that what represent what, we can directly compute this quantity. Okay, and the same thing happens for the second term as well. Okay, so this says that okay, I have p1 psi, and then this time p2 is going from here, and this contraction term comes here, and then there is another p2 term and p2 prime. Okay, so this to some extent represents that this term. So now these pictorial representations are actually called Feynman diagrams. Called Feynman diagrams. Okay? And the rules that by which we get this are called Feynman rules. And the rules are called So all this calculation that that I was pointing out earlier, that all these calculations and everything finally boils down to few branches of the contraction operator, which eventually will give us this thing, this 1 over k squared minus m squared term, and some delta functions that that actually says that there is momentum conservation, and those delta functions actually come because of the and all this comes because of the interaction terms that we have. So without going further details, let me write down the rules by which we can actually compute this. Okay. So rule 1 says for so Feynman rules and Feynman diagrams are basically from few building blocks we can actually the whole calculation we can represent via some diagram. So what are the things that we have? If we see this carefully, then we have this external lines. Those represent the initial and final state. Okay. And then we have a bunch of contraction operator which represents this internal lines or the propagators. Okay. And then the theory has interaction between these between the fields, and those are represented by these vertices between the either internal or external lines. Okay. So our building blocks are basically external lines So each incoming or outgoing state working state is represented by and we will use different lines for psi. Here we will use different line for psi and separation. Second is vertices. That is another important thing, that draw vertices representing the interaction terms. Okay. Then internal lines or propagator, which represents which has no free end to represent propagators. Okay. And in each vertex, apply conservation of pole momentum. Okay. And then finally integrate over the undetermined momentum, just like K here. Okay. So for this theory, what are the vertices and external lines? So for this theory, the external lines corresponding. So let's say for this theory, for this theory, an interaction external line corresponding to psi the assignment of psi, we will have a number 1 and external line for phi. For that also we'll put 1, and for propagator, let us represent for phi. Okay, phi. This is I over p squared minus m squared plus I over 7, and propagator for psi is I over p squared minus this is capital M squared because the mass of this particle is capital. Okay, and so this and the vertex, let's say with psi, and phi, okay, is in this case minus g. Okay, so those are the things that comes here. And okay, so this is the complete Feynman rules. And then from this, if we now try to do the whole calculation that we did for let's say for 1 hour, it will be like 5 minutes job. So let's see psi to psi going to psi to psi. So what we have to do is we have 2 initial state, 2 final state, and then we have to draw all sorts of possible diagrams maintaining these relations. So we have a vertex. Let me do this way then, and then once we have a vertex, we will have a phi field here, and then this will be contracted here. And so if we represent the initial state on the left, let's say psi, these are, let's say, initial state, then and this is psi, these are final state, then let's say p1, p2, p1 prime, p2 prime, and okay, so this momentum, since we have momentum conservation here, it's p1, let's say incoming and outgoing p2, so p1 minus prime, and here and the other way of contracting these two would be this way. Okay, psi, this is p1, this is p2, and this one now is p2, this one p2 prime, this one is p1 prime. Okay, so these are the two possible diagrams for the third term that we considered, but if we go to higher order, then we will have something more that we will not discuss here. Okay, so the whole calculation boils down to these two pictures, and then we have this rule that we have corresponding factors for all these entities here. So for each vertex we have so let's say for the first term, for each vertex I have minus ig. Okay, and let me write it as the momentum k. Okay, and since we have two vertices, minus ig squared, okay, for each of the external lines is 1, we don't have to do anything else, and for each vertex we'll have momentum conservation, meaning that all total of incoming momentum should be conserved. So this one minus k, right, and delta 4 p2 P2. So this is P2. This is minus P2 prime plus K. So assuming that this is 0, meaning that all the incoming, so P1 is incoming to the vertex, P1 prime was going outward, so that's why I had to take minus sign, and then K also had to be taken minus sign because it is going out from the vertex, okay, for the first. Okay, and then the third, so this is done, and then we have the propagator, which is I over a squared minus m squared plus I itself. And then we have the momentum integration, which is nothing but this. Okay, and from the second term is the similar, but only thing is that P1 and P2 has been exchanged. Okay, so then it will be basically delta 4. Okay, so when we do the momentum conservation, okay, conservation of moment, I basically says this is 2 pi 2 pi sum of, okay, so we will have 2 pi whole to the power 8 factor from the 2 momentum conservation, and this is from the second term. So this will not be P, this will be undetermined momentum is K here, and this is P1 minus P2 prime minus K delta 4 P2 minus 1 prime plus K by square undefined. So if you now see this expression and the expression that we derived is essentially the same, right? Is exactly the same. Okay. Except for K, that since this is undetermined momentum, we can take it upwards also, then the sign of the case will also be seen. Okay. So what I mean is essentially, if we do this way, define K this way, then this is minus and this is plus and this is minus, then you can say this is exactly the same. Okay, so that's the beauty of this Feynman diagram, that we actually can whatever we have seen, that we have to calculate a lot of algebras, commutators and all these things, but eventually this boils down to calculating some of the uh, pictures via some rules. Okay, now let me come to the case of QED, which is so this thing that that has been shown, because for a theory where everything is scalar. Okay, so now the same thing will happen, but with slightly complicated way for the QED case, where we have fermions and the and gauge bosons or the vector bosons, where the only thing that will be modified, so propagators of course will be modified, but this external line factor will be something different, because we have I mean we have a slightly different structure in front of the B dagger operator or B operator or A dagger operator that we saw. And that is why now in case of QED, if the Lagrangian, for which the Lagrangian is written as f mu nu minus psi r I del slash minus psi, and E a mu that we saw last time. So here, of course, our interaction term is this. Okay, so now for this, the Feynman rules, not derive them, are essentially that for external line, okay, for incoming photon, we will have epsilon mu p if the momentum of the external line of the photon is and then outgoing photon as this. Okay, and for incoming okay, let me write the QED part again. And the rules are for the external lines, incoming photon, for each incoming photon, we will have to put a factor of P, and for outgoing photon, we have to keep a factor of this. And for the fermions, incoming fermion, we will write U, because this is the prefactor. This is the helicity that appears just before the B operators. And for outgoing fermion, we'll have U bar B. And since the fermions are not exactly real, meaning that they have their antiparticle, so for incoming antifermion, we have a different which is represented by V, okay? And for outgoing antifermion, it will be V. Okay, so these are, let's say, some spin states. So this is something. And then we'll have propagators here. So since we have two particles, two fields, we have two propagators. One is mu, another is mu. And for each propagator, we'll have a factor of where q is the momentum. And for fermion, we have a different propagator. Okay. This, where m is the mass of the fermion, and it will be p squared minus and in this we have only one vertex, and momentum does not matter, at least in this vertex, so it will be common. Okay, so this is the complete Feynman rule for QED. And if we have some time, let me do an example calculation from QED for E minus electron scattering. Okay. So now, be adhering to these rules, we have basically two diagrams for this. One is similar to the previous. The only thing is that we now have two. Instead of scalars, we have fermions, and instead of real field, we have real scalar field. Sorry, complex scalar field, we have fermion. Instead of real scalar field, we have photon. here. Okay, so the diagrams will be exactly be the same, okay, just with this replacement. Okay. And then we'll have same thing this way one and this. Okay. So these are the vertices, and then this is E minus, E minus, E minus, and let's say momentum are K1, K2, K1, K2. These are the initial state momentum, E minus, E minus, and outgoing states are P. So this is P1 and this is P2. Only thing that will be different in this case will be the computation, which is very messy. Okay. Let me write this as the diagram 1, this as diagram 2, and then the corresponding amplitude will be Im, which I write as Im1 plus Im2. So Im1 represents this diagram, Im2 represents this diagram. Okay, and then we are kind of interested in the square of it, mod square of it, which will not be nothing but this mod square Im2 mod square plus 2 real part of Im1 Im2. Okay, so now let us try to calculate at least one part. Okay, so Im1, which represents the first diagram, is nothing. So in this case, what we have to do is starting from the Fermion line, going back towards the uh, towards the backwards of the Fermion arrow. Okay, so this is Q bar, then this is P1. Then we hit this vertex, which will have minus I e gamma mu. Okay, and then each incoming is represented by Q of K1. Right? So that's this part, the first part here. So this part here, and then for the other part, let us do the same thing. As the before, it will be U bar U2, then minus IE. Let us take this index to be new, and this index was new. Okay. So IE gamma new, and then U of K2. Right? And then we have the propagator, which is here. Okay, so this, let us call it P, which is nothing after the momentum conservation will become K1 minus P1. Okay, so it will be rule was this I eta mu nu over Q squared. Okay, so I eta mu nu over K1 minus P1. It is not right, the epsilon, you know. Okay, so now if we want to compute this, it's let me club all the I factors and make the signs. It will be minus I squared, and then K1 minus P1 whole squared, and then U bar U1 Q1, and then times U bar Q2 gamma mu Q2. Remember that these U's are actually in the Dirac fermion case, it is a 4-component spinor, and gamma has, so it basically has one index R, and then gamma has, so this R goes from, this R is goes from 1 to 4. Okay, so these are 4-component spinors, and the gamma will also have SR. So this is also a matrix, and then this U bar will also have okay. So U bar also has this. Right? The similar thing is here. Okay. Now, if we so this is fine, and then let me compute in order to get m1 square. I need minus I m1 dagger I m1, right? So let me calculate I1 m1 dagger. So it will be plus I squared over k1 minus p1 squared, and then dagger of the first term, and then dagger of this term. So okay. This part here. Okay. So now if we see this term, for example, it's it is not square. It's nothing but U dagger. So this dagger is actually on the spinor space. Since mu and nu all are indices has been explicitly specified. So this will be mu downstairs. Right? Eta mu nu has been contracted out. It is okay. And let me do one more small change. That since mu are contracted, let's say here, and so let me write it as mu prime, which is a different index from mu. Okay, it's just notation. Okay, and the repeated indices are some. Okay, so mu prime. So this is k1 dagger and gamma mu prime dagger, and then if you remember, U bar is nothing but U dagger gamma naught, then it's gamma naught dagger, and then U of P1, right? And now if we remember some more relation, which is like gamma mu dagger is nothing but gamma mu gamma naught, then we can write it as U dagger U1 gamma naught gamma mu prime gamma naught. And this same relation will give us that gamma naught is equal to gamma naught, and gamma naught squared is identity in this spinor space. Okay, so this way it's gamma naught U. Okay. Now this is essentially identity in the spinor space. Okay. So it will be U, and this will constitute U bar gamma mu prime U P1. Right? So essentially, it looks like we have to just write it in the reverse order. Okay, so minus I m1 dagger is nothing but I squared q1 minus p1 whole squared, and then u bar k1 comma mu prime u p1. Okay. And the second term, the similar way we can write as k2 bar gamma mu prime, and then u. And now if we contract these two, it will be e to the power 4 k1 minus p1 whole square. And then we have to write these two things, u bar k1 gamma mu prime u p1. So this is the first term, and along with that, I want to write the first term of the IM1. Right? So this one. So it is u bar k1 gamma mu, and then u k1 times the same thing that p2 u bar p2 gamma mu u. Now here we want to do a small trick. Let's say the second term, the multiplication. This, let us represent it as the first few, all these things will eventually, so all this thing has of course this spin indices r is SL, all these things, right? So this in this spinor space, these are actually some 4-dimensional vectors, right? And hence let me represent it as this 4-dimensional vector as u, and the rest as some w. Okay, so this, if we do this, then let us introduce some basis with completeness relations. So this is W and okay, so this is in the spinor space. So I is open 1 to 4, where EI are orthonormal. So this we can always do, right? For a finite dimensional space, we can always choose some orthonormal basis. Okay, and and in between W and U, we are inserting this completeness relation, because we know this is identity for orthonormal basis. Okay, or in other words, let's say if we just use the Einstein summation convention, then let us write delta ij W E J I. So J, this is nothing but just one of the indices has been contracted with delta ij, and this then we can write as EJU. Okay, so delta ij, EJ, remember this E's are the basis vectors. Now this whole thing can be treated as an operator. Okay, so this we already see and then contract. Now if you see the whole thing, this is nothing but the ijth element of this operator. Okay, so this can be seen as the ijth element of this operator. So this is nothing but ijth element. So if you remember that, how do we find the elements given a basis of an operator? Is this is the precise the exercise. And now this is nothing but trace of this operator. Okay, so the thing that we saw here, for example, in this expression and in this expression, okay, in both of the cases, what we can do essentially is we take this u, put it inside, then it is no longer a contracted object, but in order to do the contraction, we can take the trace. The same thing we can do for this thing. Okay? So that is the trick that we will play here, and in order to calculate this. So it will be essentially to the power 4 over then it will be trace u k1 u bar k1 gamma u prime stress not stress stress getting stressed k2 u bar and then gamma u p2 u bar p2 and then gamma. So eventually we will get this thing. And then if we remember the completeness relation for u and v's, let us write the u's. U over all sum over all helicities or spins. Okay. Then we know this is nothing but k1 slash mass, right? Where k1 slash is nothing but gamma mu k1. And so the whole expression will become so this will and it will eventually be trace of k1 slash plus m gamma mu k1 slash m trace of k2 slash gamma mu prime p2 slash plus m gamma mu. Okay. So now if we remember the trace relation, I don't know whether that has been covered in this course, but let me remind you that trace of, so remember that this K has already gamma matrices in it, right? And M comes with some identity operators, right? So eventually we have to take traces. So all these traces and everything is in the spinor space, right? So over these 4 indices that I was talking about. Okay. Now this trace with odd number of gamma matrices actually vanishes. So only even number of gamma matrices contribute. Hence, after all this multiplication, this will be boiling down to trace of. So one term that will be here is gamma prime, and then p1 slash gamma mu, and then other term. So there should be 4 terms, but 2 of the terms will have 3 gamma matrices in it. Okay, so these 2 multiplied with these 2 will become total 4 terms. But let's say m times k1 slash times gamma mu prime times gamma mu, it has 3 gamma matrices, so eventually it will become 0. Only the contributing part will be this. So this again will have trace. So this is from the first thing, and the second part it will be trace then k2 slash gamma mu prime p2 slash and then gamma plus m squared trace of gamma mu prime gamma mu. Okay, and then we will remind ourselves that trace of gamma mu is 4 eta mu, and trace of 4 gamma matrices. These are the two things that will appear: gamma mu, gamma alpha, gamma beta. You can actually remember this very easily if you have 6, 8. So take first two trace eta mu alpha beta. Then you take this one with this one, but at that point you have to take a negative sign mu alpha mu beta, and then you do this with the last one, then it will be beta mu beta, but again with a negative sign, and the negative will contribute to positive, then beta mu. Okay, so this way you can actually iterate. Okay, so this is the relation, and let me put that relation back here. It would be e to the power 4 minus p1 e to the power 4. Then from the first term, we'll have, for example, there will be one eta mu nu from this and one gamma matrix from K1 slash, and then K1 slash has a index, so it will become K1 mu prime times P1 mu, okay, minus K1 dot P1 eta mu prime times K1 mu. And then from the second trace is m squared minus eta mu prime times K2 mu prime K2 dot K2 okay. Okay, so the time is running late. Okay, let me give you the final result. So now this is like contraction of new operators and all this thing. So let me give you the final result for this calculation, at least for which I have defined is as K1 plus K2 whole squared is nothing but K1 squared plus K2 squared. So K's are the momentum of the electrons plus 2 K1 dot K2 is this imply that K1 dot, so it will be in terms of K1 dot K2, K2 dot K1 dot P1, so all sorts of dot products that will appear. So this is nothing, if we define in this way, these are called Mandelstam variables, then it is nothing but S2m squared, where m is the mass of the electron, and T is defined as K1 minus P1 whole squared, which is the full vector squared, and then this implies that Q1 dot P1 equals 2m squared minus T over 2, and U we define as Q1 minus P2 whole squared implies Q1 dot P2. So all sorts of dot products will appear, and it will be 2m squared minus U over 2, and these three are called Mandelstam Mendelssohn variables, even though we have four momentum because of the momentum conservation, we have K1 plus K2 equals 1 plus P2. So one of them is actually dependent. So in terms of this, our final expression would be S minus 2m squared over 2 squared plus 2m squared minus u squared plus m squared t plus u plus 4m squared. Okay. So this is, and for m2, if we remember, it's just p going to, sorry, p1 and p2 has been exchanged. In other words, it is like p and u has been exchanged. So for this, the expression will be sorry, t squared, u squared, and s minus 2m squared for c. U has been exchanged to m squared t plus 4 squared. Okay. And the real difficult part will be calculating this M1 dagger, M2, then we'll have trace of 8 gamma matrices. In this case, we had like 4 gamma matrices, that will have like 8 gamma matrices at max, and then we'll have 6, 4 also. And in so this, okay, this is the expression. So this is the matrix element that we can calculate. Now, what is the utility of this matrix element is that this actually represents the probability, right? That probability that we defined we said initially that we are interested in the probability of I don't know, it's not writing. There seems to be a problem. This again. Okay, in the meantime, maybe if you have questions, then I can take some questions, and then I'll take 5 more minutes quickly, and then if you have any question, yeah, in the chat or
Hello. So I have some questions. So basically, when we're doing all this process of computing the S matrix elements, like when we're solving an actual QED or QCD problem, what are the things, like we can just proceed by using the directly the Feynman diagrams, right? We should not, or we shouldn't necessarily start from the Vic expansion, and then all the stuff of the S matrix, right? All this contraction. When we're actually solving a practical problem, for example.
Yeah, so whether your question is whether we have to do the whole expansion over and over again, so in the starting phase, like yeah, so the answer is no, we don't need to do it over and over again, but you have to do it at least for once, so that you have the understanding, and if anything goes wrong, you can always fall back to your basics and redo the calculation and re-derive your Feynman codes. But in the actual problem, once it is a very established theory and all the Feynman rules has been set, then we don't need to do the thing.
But if we are, for example, working in a new quantum field theory, like for example, quantum gravity or something like that, we need to do that from scratch, right?
Yeah, from the scratch, and then you have to like derive the Feynman rules carefully, and then once those are all set, then you can forget about all those calculations and start from there.
Okay, and I have another question regarding the QED part. So if you can go further, like to point you the like up to point you my question, like the slide in which I have questions. So if you go down, like no, in the QED part, like already computing the electron scattering,
Right.
which I yes. So yeah, I have a question. Why the electron scattering has, I mean, why there cannot be also an S channel? Why only T and U channels?
Oh, so simple answer is charge will not be conserved if you take E minus, E minus. Okay, because we don't have any vertex which represent E minus and E minus. We always have psi bar sign, right? Gamma mu and then A mu, right? So interaction term. So we have to have, where is it? Here, for example, the right hand side, if you see that we don't have psi and mu interaction. We have one particle, one antiparticle, but if they are in the both are in the incoming state, then we can we have to have one particle, one antiparticle. But this antiparticle on the outgoing state will like correspond to particle because of the thing that we actually calculated in the previous example, that even though it was like psi, where is it? Yes. So here, for example, we were trying to see, okay, let me see. We're trying to see psi going to psi, right? But
Okay,
even then,
so
psi bar, yeah, right?
so in our
And
like,
then,
okay, I'm sorry. No, like actually I was wondering, so if in our Lagrangian density we have the product of two fields, then that will correspond to an S channel, right?
yeah, then it will. But in actual QED, that will not be there. There are two reasons. One is like charge is not conserved, and then if it has a zero charge, then you can actually define some term, maybe I don't know, like term, then you can do it. Otherwise, even if it does not have charge, but Lorentz index also has to be contracted, right?
Yeah, I guess also because of the nature of the interaction, two charged particles need to by force eject a photon. So if you have two non-charged particles, then how a photon could couple will be
Photon could not couple.
exactly. So a final question regarding that. So how do I know in general, just like if I have whatever process, not necessarily QED, could be whatever theory. How can I tell either if it has S, T, or U contributions? Just by looking at the Lagrangian?
Just by looking at the Lagrangian, I don't know, but by taking the Feynman diagrams taken into account, you can, maybe. But from the Lagrangian, I don't know whether it is possible.
But for example,
But,
if I have whatever scattering, and I want to draw all the possible Feynman or all the contributions to that scattering, how do I know, for example, that is an S, T, and U, or the three of them contribute?
that I think you have to do the Feynman diagram. I mean,
and then
draw the
see
Feynman.
if the charge is conserved?
For charge is conserved, yes, that you also have to see. Right.
Okay, thank you very much.
Okay, so Okay, so calculate this as an exercise. But yeah, this is really, really messy calculation because it has 8 gamma matrices. So now, as I was saying that why is it useful? Now, we started with that we wanted to see the probability of finding from initial state to final state. So probability, this is related, if we remember, to the cross sections. So this is essentially if Si. So that is why this is called the S matrix. Okay. So we write it as S, which is nothing but the thing that we discussed first. So this is if I. Okay, so this is the probability, and it is directly related to the cross section that we encounter in the scattering theory, even in the quantum mechanics, and that is related. Quickly write it. I don't have much time. As this. And this whole thing that actually comes is here. This is the thing that comes, and then you will have dP over E. And this gives that how the particles, or if there is a scattering between, let's say, incoming beams of 2 particles, for example, in the collider, and if they scatter off, then what will be the distribution of this? The differential distribution is given in this d sigma thing. And in order to calculate that and how they will be distributed, a factor that comes as this inside this probability distribution is this matrix element square, or the scattering amplitude square. Okay, and where this dpi are essentially the I 1 to n at the final state particles, and so this is called the phase space. So of the final state, and here this number that the scattering amplitude that I was trying to calculate, one for the QD and one from other theory, that comes in here. And this is one of the kind of utility and one of the computation that I wanted to show, but for the scattering I don't have much time to go into the details. So I just denote this as this E1, E2 are momentum of incoming beam, and m squared is calculated and and the thing that we want to note that there are many scattering processes and experiments, and all actually gives the result that actually corroborates with the quantum field theory calculation, starting from either if it is a QED process, and from the QED Lagrangian or QCD process, all actually corroborates with the quantum field theory calculation, and that is a very greatest success of QFT. There are many more other things, but I wanted to show that this way we define the cross section, and then this distribution actually can be measured, and they have been measured in very good accuracy in collider experiments and in other experiments also. Okay, so that's with that note, I want to, let's say, stop here. And if there are any more questions or general question that I can take, and I hope that these lectures are useful to some of you or all of you. And
thank you so much for the lectures.